directions from each other, these two. Otherwise, it's like in a regular helicopter when you spin the rotors up, it will actually start drifting sideways or spinning, rotating. That's what happens with the rotor on here. To counteract that force on a quadcopter, they just rotate, alternate the rotation direction. So basically, you spin up the rotors, this will come up. You can hover it, you can move it in any direction, or by slowing down the two opposite rotors, you can make it rotate in one direction or the other. It's all controlled by a flight controller because a human does not have fast enough reflexes to level a quadcopter. Like with the front, it'd be like pitch and roll. So that's just the direction.
The history of the quadcopters. Attempts to make quadcopters started as early as 1907 with Roget. The first successful quadcopter was in 1922. There's more advanced versions, maybe that's okay, pictures. Newest unmanned models include the 2010 Parrot AR, the 2013 DJI Phantom, and then Quadcopter is new.
It's a new manned, actually, multi-copter, actually. This is the Bouquet quadcopter. It was built in 7.
It didn't. That was quickly changed with. The box is a quadcopter. There's a video out there where we were here, just like actually flying. It's okay.
This is a military built one in 1958. Obviously one of their early experimental programs.
There's one up here.
Yeah. And this is a good one, but it's quite advanced. This is the Parrot AR drone. It costs about $300 to get it at a lot of places actually online. Bigger and monster.
It's a lot more compact, streamlined, more user-friendly.
About that big. Great. And then this is another little bit more advanced one that is coming now. It carries GoPro. It's popular among photographers and videographers. And it's the Quadcopter, which was built by a company in Germany, and it is actually the first successful electric helicopter that we personally fly. Currently it has a flight time of about 20 minutes, but with battery it's there what we might bring it up to.
Some of the math involved in this, integration and derivatives can be used to find all different things in multicopters, such as acceleration, velocity, and position, whether that's up and down, forward, backward, any which dimension. Relative maximization can be used for optimization problems such as optimal velocity,
we basically went over a basic flight that basically takes the quad off the ground, total time of 30 seconds. It accelerates up to maximum rotor speed of which is about 8,000 RPM, and just to get it off the ground, and then it'll bring that rotor speed down to 6,000 RPM, which will let it hover, and it hovers for about 8 seconds. Well, yeah, about and then it starts decelerating again, and we'll bring it back down. And our question was, how far does one of the tips of the propellers go in this time? And what power diameter of the tank.
So our question, you have to first find the number of rotations during the liftoff, during flight, and during landing by taking the integral of the velocity function of the quadcopter and then convert it to inches and feet. So our graph has 5 pieces to it. You see the next slide. And so it comes out to
This is just the integral of each
ends up as 260 rotations in 30 seconds. Multiply that by 2 times 5. You get 8,168 inches or 680.68 feet.
This is our basic graph of rotor velocity. So as you see, it goes up to maximum rotor velocity. Well, it gets up to the off the ground. Basically, it won't start lifting off the ground until here because it's hover level. And this will hover just to keep it on spot. So it will lift off, and then the rotor velocity will come back down, and it will hover in place for 40 seconds. And then it will start decelerating and down.
Yeah, all the equations are over here, not specifically in order, but
Just to keep it going.
all right. For some of our history, John Smeaton developed the Smeaton coefficient for atmospheric pressure for use in lift formulas. The Wright brothers used it with airplanes, but it was quickly revised, and later they added a dynamic pressure variable to the lift formula. So they still helped with the Wright brothers and all sorts of developments in aerial machines.
Newton, as the fathers of this, created integration.
These two handsome notes right here. Newton 1666. I've invented calculus. Leibniz 1674. I've invented calculus. Really? Sounds a little bit derivative.
Okay, there are a multitude of applications of math in motor rotors, which include lift, which volume emitter, or the rotors, navigation, time remaining, relative velocities, precision triangulation, point path optimization, etc. Battery weight power density optimization. So, like, if you take too large of a battery, you will not if you the larger the battery, the longer the flight time, so you really want to optimize that. If you can take the rotor velocity down to about 80%, that's optimal.
Yep. When you can hover at 80% of the maximum speed of the motors, then that's as efficient as you can get. So, but in general, it's linear. Like battery life is better up to that 80% mark. So more battery means better flight.
Smart applications, autonomous balance, basically uses multitude of sensors that are in there, rear, gyroscope, accelerators, and rotor velocities to calculate the exact value and some optimization.
Some applications in the real world include aerial photography, like you saw with the DJI Phantom, drone journalism, hobby flight, which is what this one's for, police surveillance, industrial inspections, and military use, and the other sort of surveillance.
There's a lot of people that are nervous about drone surveillance, but it really isn't very well organized. They have actually saved the life of